Welcome to yet another episode of Computer Graphics. Myself, Fazira Razak Hamza, Assistant Professor in PG Department of Computer Science. And I am here to present on the course Computer Graphics. In the previous episode, I have been explaining about video display devices. Here in this episode also, I am going to continue with the remaining video display devices. Okay, so let's start with the first video display device, that is DVST, Direct View Storage Tubes. An alternative method for maintaining a screen image is to store the picture information inside the CRT instead of refreshing the screen. A DVST stores the picture information as a charge distribution just behind the phosphor coated screen. That means it is being stored inside the CRT. There are two electron guns which have been used in DVST. One is the primary gun, which is used to store the picture pattern. The second is the flood gun, which maintains the picture display. Like every other display devices, DVST has both advantages and disadvantages compared to the refresh CRT. Let's move on to what are the advantages. Since we already said refreshing is not needed here, right? So, very complex pictures can be displayed at very high resolutions without flicker. So, what will be the disadvantage? Disadvantage is that they ordinarily do not display color and that selected parts of a picture cannot be erased. So, to eliminate a picture section, the entire screen must be erased and modified picture is redrawn. That is the disadvantage in DVST. Let's move on to the next video display device, that is flat panel displays. Let's see what is flat panel display. There are first a class of video devices that have reduced volume, weight and power requirements compared to a CRT. See, a significant feature or an important feature of flat panel displays is that they are thinner than CRTs. For example, TV monitors, calculators, laptop computers, pocket video games are some of the examples of flat panel displays. Now we can separate flat panel displays into two categories: emissive displays and non-emissive displays. Okay, so let's see what is emissive displays. Emissive displays or emitters are devices that convert electrical energy into light. See here, plasma panels, thin film electroluminescent display and light emitting diodes are examples of emissive displays. Let's first move on to what is plasma panel. Plasma panels, also called gas discharge displays, are constructed by filling the region between two glass plates with a mixture of gases that usually includes neon. Let's see the working. A series of vertical conducting ribbons is placed on one glass panel and a set of horizontal ribbons is built into the other glass panel. Voltages are applied to a pair of horizontal and vertical conductors which goes the gas at the intersection of the two conductors to break down into a glowing plasma of electrons and ions. Picture definition is stored in the refresh buffer and the voltages are applied to refresh the pixel positions at 60 times per second. Separation between pixels is provided by the electric field of the conductors. This is how a plasma panel looks like. You'll be having a Like I said, you'll be having a vertical conducting ribbon and a horizontal conducting ribbon. They are conductors and there is a gas known as neon in between the glass plates. Okay. One disadvantage of plasma panel is that they are strictly monochromatic devices, that they can only display one color. Moving on to thin film electroluminescent display. A similar in construction to a plasma panel. The only difference is that the region between the glass plates is filled with a phosphor such as zinc sulfide doped with manganese instead of gas. When a sufficiently high voltage is applied to a pair of electrodes, the phosphor becomes a conductor in the area of the intersection of the two electrodes. Electrical energy is then absorbed by the manganese atoms, which then release the energy as a spot of light. So that electroluminescent displays requires more power than plasma panels, and good color and grayscale displays are hard to achieve. Third type of emissive device is the light emitting diode LED. Here, a matrix of diodes is arranged to form the pixel position in the display, and picture definition is stored in a refresh buffer. As in scanline refreshing of a CRT, information is read from the refresh buffer and converted to voltage levels that are applied to the diodes to produce the light patterns in the display. Next, we'll move on to non-emissive displays. Non-emissive displays or non-emitters use optical effects to convert sunlight or light from some other source into graphics pattern. Here the most important example is liquid crystal display device. See, LCDs are commonly used in small systems such as calculators and portable laptop computers. These non-emissive devices produce a picture by passing polarized light from the surroundings or from an internal light source through a liquid crystal material that can be aligned to either block or transmit the light. So we can either block or transmit the light using the liquid crystal material. The term liquid crystal is because these compounds have a crystalline arrangement of molecules, but they flow like liquid. This displays commonly use nematic liquid crystal compounds. Nematic means thread-like, and they tend to keep the long axis of rod-shaped molecules aligned. Here also there are two glass plates, each containing a light polarizer at right angles to the other plate, sandwiching the liquid crystal material. Rows of horizontal transparent conductors are built into one glass plate and columns of vertical conductors are put into the other plate. The intersection of two conductors defines a pixel position. This is how an on state and off state of a liquid crystal display looks like. Okay. Now let's move on to the next display device, that is 3D viewing devices, that is three-dimensional viewing devices. See, graphics monitors for the display of three-dimensional scenes have been devised using a technique that reflects a CRT image from a vibrating flexible mirror. Let's see how it works. As the varifocal mirror vibrates, it changes focal length. These vibrations are synchronized with the display of an object on a CRT so that each point on the object is reflected from the mirror into a spatial position, corresponding to the distance of that point from a specified viewing position. This allows us to walk around an object or scene and view it from different sides. Let's see the figure. See, there is a CRT from which we are making a display. And from the view of the CRT only, a viewer is viewing the 3D object. There is a rabbit, which is the projected 3D image, and there is a vibrating flexible mirror. Okay. Now, these vibrations are synchronized with the display of an object, and it is being recorded with a spatial position. So, this is how a three-dimensional viewing device works. Now, we have the next display device, that is stereoscopic and virtual reality system. Let's see how a stereoscopic or a virtual reality system works. Another technique for representing 3D objects is displaying stereoscopic views. This method does not produce true three-dimensional images, but it does provide a 3D effect by presenting a different view to each eye of an observer, so that scenes do appear to have depth. So, scenes do have a depth in that. To obtain a stereoscopic projection, we first need to obtain two views of a scene generated from a viewing direction corresponding to each eye. Each eye means the left and the right eye. We can construct the two views as computer-generated scenes with different viewing positions. Or we can use a stereo camera pair to photograph some object or scene. When we simultaneously look at the left view with the left eye and a right view with the right eye, then the two views merge into a single image, and we perceive a scene with depth. To increase viewing comfort, the areas at the left and right edges of this scene that are visible to only one eye have been eliminated. See, let's see a stereoscopic projection. It is how it looks like. See, we'll be looking with two different eyes, that is left and right. But when we simultaneously look at the left eye and when we simultaneously look at the right eye, these two views merge into a single image. Okay. This is how stereoscopic projection works. So one way to produce a stereoscopic effect is to display each of the two views with a raster system on alternative refresh cycles. We'll be providing refresh cycles and we'll be viewing with a raster system. The screen is viewed through glasses. See, the person in the image, the person who is seeing a 3D object is wearing a glass. So the screen is always viewed through glasses with each lens designed to act as a rapidly alternating shutter that is synchronized to block out one of the views. See, this is the glass for viewing a stereoscopic scene. Okay. I only said about stereoscopic viewing, right? I already said the topic was stereoscoping and virtual reality system. Now let's see how stereoscopic viewing is being a component of virtual reality system. A headset containing an optical system to generate the stereoscopic views is commonly used in conjunction with interactive input devices to locate and manipulate objects in the scene. Here is the headset which we use with stereoscopic viewing. A sensing system in the headset keeps track of the viewer's position so that the front and back of the objects can be seen as the viewer. Thank you so much. We'll meet in the next episode. Thank you for listening.